Welcome to this explainer. Today, we're diving into a fascinating mechanical secret that is basically hiding right in plain sight. We are going to look at the hidden muscles that literally power our modern world. We're talking about actuators. You know, if you've ever stopped to wonder how heavy industrial machinery moves with such incredible precision, or honestly, even something as simple as how the disk drive in your computer slides open, well, the answer lies in these absolutely ingenious little devices.
Here is our quick roadmap for today. We're going to start by meeting the machine muscle, then check out some actuators out in the wild. We'll follow that up by breaking down linear actuators, then rotary actuators, and finally, we'll do a side-by-side linear versus rotary breakdown.
All right, let's jump right into section 1, meet the machine muscle.
Think of it kind of like this. If a machine is a body and its internal computer is the brain calling the shots, the actuator, well, that's the muscle doing the actual heavy lifting. Technically speaking, an actuator is a component of a machine or a device that achieves physical movement, and it pulls this off by transforming energy, usually electrical, air, or hydraulic energy, straight into mechanical force. So in a nutshell, if a machine has a part that permits motion, you are looking at an actuator hard at work.
Moving on to section 2, actuators in the wild.
These devices are just incredibly versatile. You will find them managing automated fluid flows in massive underground pipelines and adjusting heavy industrial valves. They provide the brute, raw strength you need for things like mining excavation and metal forging, but at the exact same time, they offer the delicate precision required for automated robotics and intricate conveyor systems. They're controlling the air and internal combustion engines, spinning power plant turbines, and yeah, they're even operating those basic automatic doors you walk through at the grocery store every single day. They are literally everywhere.
Which brings us to section 3, linear actuators and straight motion.
So one of the absolutely most prevalent design functions in all of engineering is linear movement. A linear actuator's entire purpose in life is to move a certain distance, and then stop. That's it. It's a simple push or a pull, just back and forth. But what's truly amazing is the scale at which they operate. You'll find these providing straight-line motion in the most sophisticated, massive industrial machinery, all the way down to the tiny, super precise movements happening right inside your PC or your gaming console at home. If we break down the physical anatomy of how this straight-line motion actually happens, you basically have a piston housed inside a cylindrical barrel. Energy gets introduced through either the cap end or the rod end ports. That energy forces the internal piston, along with the attached piston rod, to extend or retract in a perfectly straight line, and it's all safely guided and secured by the tie rod. A classic, everyday example of this linear design is the piston used in traditional car engines and pumps.
But what exactly is in there pushing that piston? Well, these mechanical muscles run on a few different diets, so to speak. They can be driven by electricity, which is generally your go-to when you need extremely precise control over the movement. They can also run on hydraulic fluid or air. For instance, manufacturers like W.C. Branham make these great low-pressure hydraulic and pneumatic models that are small, super dependable, and really economical to run. And hey, if you need some serious power, a pneumatic actuator driven by air can provide defined strokes, incredibly fast response times, and exert massive forces of up to 4,000 pounds. To put that in perspective, that's like lifting a mid-sized SUV.
Now that straight line motion is absolutely great for pushing and pulling, but here is a fun engineering problem for you. What if your design calls for an angular travel path? What if you need to, say, lift and turn a product to keep it moving at a totally different angle? Or maybe operate a swing gate on a conveyor system to redirect a package? A straight line just won't cut it there.
And that solves our mystery for section 4, rotary actuators and circular motion.
While linear actuators always move a certain distance and then have to stop at the end of their track, rotary actuators play by a completely different set of rules. They aren't limited by the distance they can travel. Instead, they are engineered for endless, repetitive, continuous spinning. Just like their linear cousins, they can be powered by electricity, hydraulics, or pneumatics, but their output is entirely rotational. The absolute most common, everyday illustration of a rotary actuator? That would be your classic electric motor.
The contrast between the two is super distinct, right down to their fundamental shapes. A linear actuator has to be built long and straight to accommodate that rod extending back and forth. Conversely, a rotary actuator is compactly designed around a central axis, so it can just keep spinning and spinning. It's really just two entirely different shapes designed for two entirely different physical tasks.
Let's wrap things up with section 5, a direct linear versus rotary breakdown. Mechanically, it's their paths that define them.
Linear motion provides that back and forth path. Think of sliding grocery store doors or the vertical drop of an elevator shaft. Rotary motion relies on a continuous circular path, driving things like wheels, gears, and cooling fans. To make this happen, linear systems use cylinders and linear motors, while rotary systems rely on electric, hydraulic, or pneumatic rotational motors.
When we look at their typical real-world applications, the differences are just as stark. Linear actuators are the absolute backbone of CNC machines, linear transportation systems, and heavy hydraulic lifts. The output here is measured as linear displacement, which is just a fancy way of saying distance, and it is generally pretty easy to control and measure. Rotary actuators, on the other hand, are powering your hand drills, large electric motors, and the drive wheels of those conveyor belts we talked about. Their output is angular displacement, measured as an angle, which might actually require some extra mechanisms to get truly precise control.
In our daily lives, it's simple. Linear motion pushes your desk drawers open, while rotary motion lets you turn your car's steering wheel. But in the cutting-edge world of robotics, this is where the magic happens, and these two combine. Linear actuators are what extend robotic arms outward, while rotary actuators act as the joints, giving them that flexible rotation. It is the careful, highly engineered combination of both that achieves truly lifelike, fluid movement.
We've seen how these devices act as the hidden muscles of our world, seamlessly translating energy into straight lines and endless circles. But here is something to really chew on before we go. As automation advances at just lightning speed, how will the perfect, seamless combination of these linear and rotary muscles dictate the future capabilities of modern robotics? When we can perfectly mimic the pushes, pulls, and rotations of the human body using these exact actuators, what completely new mechanical wonders are we going to be able to create?